Welcome to Closing the Loop, podcast presented by Lakeside Process Controls, where we connect you with experts, end users, and suppliers in the industrial automation industry. My name is Justin Kozak, business unit lead for measurement solutions at Lakeside and host of the show. Each episode will be featuring special guests from Lakeside Process Controls, Emerson Automation Solutions, and other industry leaders. We hope that through these conversations, we can close the loop between your current knowledge and the latest advancements in industry. Our goal is to educate, provide you with ideas on how to improve efficiency and safety throughout your facility. And with that, I'd like to introduce you to today's guest, none other than Lakeside's very own Looney tuner. Welcome to the show, Sylvain Millette.
Thank you very much. It's great to be here. It was one of my first experiences doing this, so thank you very much for having me.
I can't believe it took up to 6 episodes to get you on.
Yeah, I've been kind of a busy person lately, so I've been very, last over a year and a half, it's been nonstop, just working in different sites and all the time.
Lots of travel?
Lots of travel, yeah, absolutely.
But you enjoy that?
I do, actually. I do like to go to site, and I just like to be on site and get my hands dirty, my shoes dirty. You should look at my my work boots. They're all encrusted of different types of whatever industrial material that's out there. Absolutely.
Oh, I know about that. I've lost a few laptops.
Have you? Yeah.
in my day already.
Yeah.
Yeah.
Oh, no kidding.
Yeah.
Wow.
Carbon black seems to be.
Carbon black is the best. Yeah. As a matter of fact, actually, I'm going to carbon black plant at the end of the month, I believe.
Is that right?
Yeah. It's going to be in Colombia.
Wow.
Cartagena. Yeah.
That's a bit far.
It is a bit far, yeah. So I did some work for the plant in Sarnia, and then they decided that, we got a plant in Cartagena, it's very similar. We want you to do the same work there.
Wow.
Yeah, so I'm pretty excited. We haven't picked the dates yet. I'm actually going there tomorrow to probably just do some prep work. There's a lot of pre-work to be done, on-site to be work, and then post-work after that. So
I feel like you're going to time it right for the first snowfall.
I hope so. Yeah, it's going to be end of October, early November. So that's usually when we hit our first snowfall. Absolutely.
Push it to January, February.
Yeah, exactly. Well, then they said, we got another plant in Argentina. We got a plant in Mexico. So I have no idea. So hopefully I'll just...
That sounds like a great spot. I remember one time getting a request. Somebody was doing tank farm upgrades throughout the Caribbean islands.
Oh, yeah.
And I think they had done St. Lucia, and they were looking at St. Bart or something like that.
Yeah.
And so they use our tank agent equipment.
Right.
And I said, I will absolutely be there for startup support, commissioning, troubleshooting. Drop of a hat, I'll be down there as needed. So, anyways, you know what? Let's get into who you actually are and your background first, just so for folks who don't know you.
Sure.
Maybe you could do a little bit of history.
Yeah. I grew up, parents, I actually was born in Africa. Actually, I was born in Togo. And my parents were there. My dad was working for United Nations.
Okay.
And doing in Togo doing soil mapping. My dad was a soil expert, so a PhD soil expert in doing soil mapping. We're there for 3 years, and then I was born. We're there from 61 to 64. So people are going to guess my age. I was born in 63. And so they left with 4 boys and came back with 5 boys. And came back to Canada. My dad became a professor at McGill University, McDonald College, which is the agricultural branch on the West Island. Those of you who know where that is. And so obviously we all went to McGill University. My tuition fees were $234.
In total or a year?
Per year.
I'll take it either way.
It doesn't really matter at this point, does it? You're right. Yeah, $234. I was staff-dependent bursary and everything else. So yeah, so I think it's amazing. And then after that, graduated in 1986, a Bachelor of Electrical Engineering, or B.Eng Electrical Engineering. Then moved to Toronto in 86, after graduation, and then really haven't left ever since. So been in the field of process control, optimization, troubleshooting, whatever you want to call it, since about 1988. So that's what, 24, 25 years?
We don't need to do math.
35 years.
Okay.
35
a while.
years.
It's been a while.
A long time. Yeah, exactly. 35 years. Yeah.
Wow. So you've had quite the experience. You've probably seen a lot of change in the past 35 years.
Yeah, I have. Yeah, absolutely. Anywhere from going from just standard electro-pneumatic position or just pneumatic positions now to DVCs that are like little mini computers on their own. So, and all the diagnostics that go with it. So yeah, it's been quite the change. And there's been some trends that have come and gone as well. And so it's been, I was also self-employed for 17 years before I joined Lakeside. So I joined Lakeside in 2011. It's been probably, of all the decisions I made in life type of decisions I've made in my life, it's probably one of the best ones I've made. So I'm pretty pleased to be doing that. So
that's awesome to hear.
Yeah.
So when you were growing up, how long were you in Togo for?
We were there for a year.
Oh, okay. So you don't remember it.
I don't remember it, but I do. So every summer, my dad being a professor would take consulting contracts throughout Africa. So we went to Benin. Back then it was called Dahomey. So spent some time there. Tunisia, Niger, Burkina Faso, Upper Volta, which is now Burkina Faso, Guinea-Bissau, Portuguese Guinea, Chad, and Guatemala as well. Spent 6 months in Guatemala in 78, 79.
Oh, wow.
Yeah, that's where I learned to speak Spanish there.
I was going to say, I could tell, you definitely speak a few languages, right? So
I speak reasonable Spanish. So in Cartagena, it's got to be, it's got to push me to actually kind of, use it and so forth. And looking forward to. Usually when we go to like vacations, it takes me about 2 or 3 days to get the ear going. They tell me I speak very clearly. I speak a very good Latino accent, they say. But apparently, the ear is, they respond to me very quickly. And I said, no, you got to slow down. Despacito. Despacito para mí.
Well, I guess the hard thing is that, it's one thing too when you go away on vacation and it's, dos cerveza, por favor. But once you get to, and you're talking about an industrial process and loop tuning, that's a whole other beast.
Yeah, exactly. It's a whole different vocabulary that I didn't have when I was 16. So
trying to translate. I don't really know the translation.
Well, that's why I got to have, at least we have a Google Translate. So, but I'll do pretty good. Actually, I already had my first meeting in Spanish.
Oh, wow.
About a couple of weeks ago with the people at the plant. Yeah. So, So I'm told in Colombia there are two accents, the costeño accents. One is the coastal accent, and montañero accent, which is the interland. And what happens is that the montañeros speak really more clearly. I'm probably insulting someone there, but and then in coastal accent, they kind of not slur the words, a little bit like maybe like French Canadian to France. So we kind of different expressions. And so I remember the one fellow was actually speaking pretty clearly, and I told him to speak slowly. The other one could not understand.
No.
It's just one long syllable.
Didn't work.
One long syllable, yes. I said, fortunately, there was a corporate guy there, and he said, can you translate that for me? Because I didn't get that. So, but I did okay. So, and I'm looking forward to it, actually. It's got a little different challenges there.
Well, the technology has changed too, right? Like when we travel abroad, now that they have Google Translate, that's one thing, but they even have the photo version too, right? Where you can look through the camera and you can see like words in live translate.
Oh, really? No, I have not seen that.
It's handy. I'll show you after.
Yeah, you're going to have to show me that.
It's like for a menu, for example, you can look in live time and it'll change all the font so that it says the English word.
Wow.
Yeah. I mean, like it's okay sometimes, right? Like I remember it trying to translate honey from German to English, and it was I forget what it said, but it's something death, and I thought, I don't know if that's the right. I hope that's just honey, right? I don't really know. It looks like it's honey. It's got a bee on it, so I'm sure that's fine. So, but stuff like that is definitely helped me.
Yeah, absolutely. Lifetime, right? It's pretty interesting. No, I did not know the. You have to show me that definitely.
Yeah. So when you're growing up, right? Did you always want to be the Looney tuner, or what kind of drew you towards this?
That's I grew up in a very, very kind of scientific, technical family. So my dad was one of the first ones to. Traditional French Canadian families back then didn't put a lot of emphasis on education, things like that. You either became a priest or a notary, something like that. And then my dad was the first one to go to university in his family, let alone get his PhD. And so to me, it was just never a question. My oldest brother was a biologist, had his master's in biology. My other one, agricultural engineering, has a PhD in agricultural engineering. My other middle brother, is mathematics, a master's in mathematics.
Oh, wow.
My other brother is a chemical engineer. So I don't know. I just said, I'll go electrical enginger for some reason.
Change it up.
Yeah, exactly that. So so I ended up going to McGill, and I don't know. I did have kind of a fascination, but I really did not know. I mean, university, what do you know in university? Other than the fact that we know everything, right? When you go to university, we know everything.
Yeah,
but we actually know nothing, right? I was going to swear there, but I'm not going to swear.
Look at that. We're doing so good.
Yeah, exactly. A little switch came on. Yeah. But we know nothing, right? And so, but I always kind of, in some ways, kind of fascinated by the self-regulating nature of loop tuning and process control, PID control. But I really did not get any kind of that. I always kind of interested. And then when I got one of my first jobs with a company called H.A. Simons, which is, I don't know, probably multiple iterations of engineering company now, I ended up doing some work for Labatt.
Oh, okay.
Yeah, beer making. So
That's
Labatt, and that's where we actually started working on the Bailey Net 90, not the infant, the Net 90 back in 1980s, mid-80s. And so I did some programming, and I thought this is kind of interesting. So I did some of that work. And then after that, I joined a company called, I think back then was Valmet Automation. So it was Valmet, basically.
Yeah.
Kind of changing names again, but on paper machine control systems. And then I ended up getting a job with Entech. So Entech now is actually, Emerson bought Entech back in 2000.
Okay.
But back then, so it was Entech. And my mentor there, Bill Bielkowski, very, very, very intelligent man. And so we used to do a lot of, go to paper mills, a lot of paper mills and pulp mills and do control audits, and really pioneered a lot of the, some of the findings that we actually apply now. For instance, in talking control valves, we actually ended up determining that control valves has a very direct impact on process variability, on process stability, and so control. Valves. What I say now, valves have to be properly specified, installed, and maintained, or precise, dynamic, and properly sized. And so valve precision became very, very important, and to get good control. So I was with Entech for about 4.5 years, and then I was doing a fair bit of traveling, and that was in a previous life, and it kind of took its toll a little bit. So I ended up actually taking another job, and then that job got. Actually, I can say this. I was working for a company called Dick Engineering. So I'm sure, have you heard of Dick Engineering?
I feel like I have.
They're actually out of, they were out of Toronto. I think, once again, they've probably been bought and merged and things like that. And so at that point, that company was bought by another company. That company was going bankrupt. So we ended up finishing a project, and I ended up being self-employed. And that's how I became self-employed after that. So, and for 17 years from then on, from 1992, 93, from 17 years onwards, I ended up being self-employed. Yeah.
Oh, wow. It's very entrepreneurial.
Yeah. It's, I'm actually, there's things that you discover about yourself like that, is that one of the things is that technically, I feel like I've got experience. I know my stuff. I'm a terrible businessman. Terrible businessman. So usually, and that's what I kind of discovered. So sometimes, some periods you're doing really, really well, and sometimes you weren't, and you always ended up, traveling a fair bit. So it kind of, after a while, you kind of get tired of the roller coaster.
Yeah, definitely.
And that's how I joined Lakeside, and that's why I say, wow, we got benefits, and something called vacation, where you can take time off and still get paid.
Yeah.
Whereas because when you're self-employed, what happens is that when you're self-employed, you take time off. Well, it costs you two ways. You're not charging, and you're spending money.
Yeah.
So it's a little bit different. So like I said, I don't miss those days at all. I really, they say you don't get rich working for somebody else, but you don't get poor working for somebody else either. So
well, I feel like especially nowadays, entrepreneurship is a little bit over glorified, right? I don't think everybody's cut out necessarily to be an entrepreneur, and it's not necessarily a bad thing if you aren't, right? Like if you don't have the affinity for that or the enjoyment, and there's other benefits, and you can still be entrepreneurial within an organization.
Exactly.
Right?
Very, very good point.
You can still kind of get that itch scratched there without all these other risks and unnecessary.
Well, I see that with yourself, and I do kind of do my own little thing as well within Lakeside, and we have the luxury to be able to do that, and so the culture allows us to do that, right?
Oh,
to
definitely.
be able to take care of our own business, and absolutely.
Yeah, that flexibility and the autonomy, I feel like that's what, and to kind of do, and be supported with whether it's a podcast or our webinars that we like to do, or right, wherever kind of the direction we want to go, we're supported. So you get that kind of piece of that. So that's awesome. It's bringing back a lot of memories here, because I studied chem eng in my undergrad, and I remember in the last couple of years we got really into well, basically all about the loops and PI, PID.
Right.
And I always had a ton of fun with that because I really like the math side of it.
Oh, did you?
Yeah.
You're one of the few. Wow, holy crap.
I didn't say I was good at it.
Yeah.
But I definitely enjoyed it. And I don't know.
Where'd you go to school?
McMaster.
McMaster, okay.
Yeah.
Usually there's a very good program there. I've met some people. I know a lot of people who are from McMaster. Very strong process control department there.
Yeah. Well, and it was kind of funny too because, that's what I wanted to do. Right.
Right.
I'm like, well, this is so cool. And
Yeah.
then I remember being told, well, you might not be able to find a job in process controls. And
Really?
I know. And I said, oh, well, that's kind of a bummer because
There's a shortage. There's probably two best jobs around you can have. One is a good control person. So we call it distributed control system. So the controls part, not the system part, but the controls part. They're hard to find. And the other amazing job that you can have, the best amazing jobs you can have, is being an instrument mechanic, instrument tech.
Oh, totally.
It's probably one of the
Short demand too.
Sorry,
high demand and short supply.
Short supply. I mean,
Totally.
I tell anyone, go into instrumentation and be able to work around the world. You'll be able to do interesting work, and you'll be able to actually cover. It covers so much. That's what That's what I like about the field of process control, instrumentation, and all that stuff. You got to know a lot about a lot of things.
Yep.
And I always say that you got to know a lot about a lot of things. You got to know, first of all, you got to know your process, right? And where you got to know your process, the different types of processes. Are you heating something up? Are you cooling something down? Are you mixing a reaction, diluting, concentrating, all that good stuff. If you don't, you got to understand the basics of the process and the process dynamics. How does a process behave? And then after that, from a controls point of view, after that, you need to know, well, how am I going to control this? Are we going to put pressure controls, flow control, override controls, feed forward control, advanced controls? And then after that, you got to look at your the instrumentation. Yeah. So I'm kind of doing my little pyramid thing that I kind of usually do at the beginning of my courses. And so I would say, so we have to understand, on the one side, we got to be able to see the process. So there we have to have the proper instrumentation properly, again, specified, installed, and maintained. So people obviously want to say, hey, Justin, I want to measure this flow. Well, you got to go through all the different questions before you pick the appropriate technology. And obviously, it's got to be installed properly, and then that's a big challenge all the time. You see, especially of all the ones that are probably not installed properly, got to be flow measurements. That's my experience. You see it all the time. What they do is that the process person or the piping person says, okay, well, I need a flow, I need all that. So they call up Justin. Justin, what are the dimensions of your magnetar? Oh, it's about 35 centimeters. Okay, so therefore, we'll put that gap in the piping, put a piece of wood there, so then we'll keep on building our process. And I just saw this just recently. And then, so then you show up with your magnetar, and then you see that it's flanged to an elbow. There's your gap. Well, the process is already built, right? Yeah. So we're the last ones in, right? A lot of the time from the instrumentation side. So we're the last ones in. And so what happens is we don't install them properly. And then from there, what do? Well, you got to compensate for it. So usually you put some signal dampening or filtering to compensate for the noise. And so now we lose any kind of dynamic value out of the measurement. On the other side, as I talked about, valves have to be precise. So we talked about precision. Back in the day, if I saw 1% precision, meaning if I increase the output by 1%, I want to see a change in my valve. And then if I decrease the output by 1%, I want to see a change in my valve. If I saw 1% back in the late 80s, early 90s, I was a very, very happy camper. Very happy camper. I couldn't believe it. So then nowadays, I expect like 0.5%.
Oh, wow.
0.5%. So, and do we always see that? No. Depending on multiple factors, the type of valve, the type of positioner, how the actual valve is actually linked to the actuator. Mm-hmm. Anytime I've just seen this one brand new facility where every single valve, not every single, but systemically, a high number of valves all had 2% hysteresis.
Oh, wow.
Hysteresis or backlash. So hysteresis or backlash is basically mechanical play within the valve mechanism. So the positioner was working on the position of the actuator but the linkage between the actuator and the actual valve position was loose. And therefore, you would have 2% hysteresis. And then what would happen then, the controller will just oscillate, would just bounce across, play ping pong across the dead band. And the PV, the flow, the pressure, whatever, would oscillate. And then that would propagate a variability. And then somebody else then had to handle that. And it had 2%, and it just kept going down.
Cascades down from
all
there.
the way down from there.
And so you're talking about the valves not coming back to the same position every single time.
Correct.
Slightly
exactly
off. Could be the same, could be slightly off, could be slightly more.
So there's a 1%, and like in this case it was a 2%. I've seen up to 3 or 4 or 5% in precision.
Wow. What it's I've had customers say, especially depending on the industry, right? Some industries don't necessarily require a high level precision. So they might say, hey, if you give me, they said, if I got 95% on a test, 98%, heck, 90% on a test, I'd be pretty happy.
Right.
So what do I care if your measurement's 0.04% or 0.004%? But I think it all just stems from there, right? Then you have all these other issues that you have to, add into that, that then compounds, and it could be a significant impact to your process.
Absolutely. It'll have what are we looking for? A lot of time there's multiple objectives, but one of the objectives also, especially manufacturing something, is you want something with consistent properties, right? Product uniformity, quality, back in the late 80s, they were talking about quality this and quality that. So it was to be able to actually manufacture a product. You got a whole bunch of incoming variability. You look at it like a paper mill or recycling paper mill, where you got recycled boards coming in. Well, they all got different kind of property, different kinds of amount of dirt, fiber length, everything else. And you're trying to output a product that actually has uniform properties that your customer is going to want to buy, and maybe even pay a premium for that quality as well.
Definitely. I like to use cookies as my analogy. I think those are more fun. You want to make sure the cookies that you're buying in the bag are the same size, they're not burnt, they're not too soft, they're the exact same cookie every single time.
Exactly, absolutely. And that's consistency is really, really important there. Absolutely. So then after that, then properly sized. The valve has to be properly sized. We tend to be scared and timid, just in case we tend to oversize our valves.
Oh, for sure.
Often.
Yeah.
And I would say the lazy person's way of sizing a valve, well, you got a 4-inch line, put in a 4-inch valve, right? And what happens when you do that is that now you increase what I call the process, technically it's called a process gain. I call it process sensitivity because I don't want people to confuse it with controller gain. So that's why I call it process sensitivity. And what happens when you oversize control valves is that now a small change in your control valve output, they say a 1% change, causes a big change in your process. And that's not a good thing, because now suppose I do have a small problem on my control valve, will get amplified onto my PV. So a little small problem becomes a big problem, and that's why we really got to be careful when we size our control valves.
It's like tapping the brakes and your car comes to a slamming halt.
You got it. You got it. Or like a hot water, 1 millimeter here is too hot, 1 millimeter there is too cold. And so it's exactly that. You can never get it right. So you end up bouncing around. And the other thing, when I talk about control valve sizing, if your control valve spends most of its life 25% open or less, that's another sign your valve is probably oversized as well.
Well, I think, you've kind of talked a little bit about pulp and paper. I think that's a good example where sometimes the process changes over years, over decades, right? And I don't necessarily know that everybody is aware of how much those, in the 80s and 90s for pulp and paper versus, 2023, there's definitely different demands, right? And so if you have the same plant, the same size lines, and you're not ripping through as much steam, right? And you're on the lower ends of these ranges, all of your flow meters, your valves, everything else is going to be in a totally different end of things, which has not been optimized for.
Exactly.
Right. And so I don't know if it's a pride thing or sometimes they don't want to admit that, no, we 100,000 pounds an hour, but it's like, well, I think it's closer to 10,000 now.
Exactly. You see that actually there's one paper mill that started back in 2006. And I think back then it was designed for probably close to maybe 800 tons a day. And now they're producing over 1,000 tons a day. So that's a 25% increase. Yeah. If my math is good. So yeah, absolutely. And then you're still stuck with the same tanks. So now the retention time in your tanks are different or a lot shorter because you're screaming the product faster. And especially in pulp paper, agitation is always very important. But now you don't have as much agitation, residence time, so therefore some variability can pass through that wasn't there before.
Yeah, that makes sense.
Yeah.
Okay, so let's just kind of go back to, maybe we'll start at some basics of loop tuning and where you get involved. So we've kind of talked a little bit about instrumentation and control valves and then the distributed control system. Where's the place for loop tuning, right? What's the need? What's the outcomes you're trying to achieve? Is it done for every single loop?
So when I teach my loop tuning course, the first thing I say is loop tuning is the last thing you do.
Yeah.
Okay. So I just went through the due diligence, and I've always approached any kind of customers call me up, say, hey, I got some work for you. The first thing I do is I walk down the process. I got to look, see, scratch, sniff the process, look at it, understand the line sizes, everything else. So once you do that due diligence, then you can assess whether or not, okay, like these valves I was telling you before that had 2% hysteresis, I didn't even bother tuning them. It didn't make any sense because they're going to oscillate. Depending on how you tune them, you're going to oscillate at different frequencies. There's nothing you can do. You got to fix the problem at the source. So once you got a decent process, yes, you obviously control tuning. You got to ask yourself then, no loop is an island unto itself, meaning that you can't just tune a loop by itself and ignore the rest because all the loops have interactions, have consequences downstream and upstream of the process, and ancillary probably sideways as well. So you got to look at your, the role of that control loop, understanding your control strategy, the process, everything else, and say, how am I going to tune this control loop? So sometimes we want our control loop to respond, I want my loop to respond as fast as possible. And that's not always the case because sometimes, especially you got interacting loops. So you got loops, let's say like pressure and flow. So they're control loops that are interacting. Any change by the flow or affect the pressure, change of pressure affects the flow. And so there you have to determine, you say, okay, well, this is the way it is. Which one of these is going to be the primary loop in terms of which one's going to be the winner, which one's going to control a lot tighter, whereas then that means you have to sacrifice the performance of the other one to minimize the interaction. So it will control, but not as fast, and any kind of actions that slower control loop will do be slow enough that the winner loop will actually be able to compensate for it. So you got to look at the entire thing to be able to assess how you should tune it. Now, other ways of tuning, I got to say that the most popular tuning method out there, probably tuning method out there is tune by feel. So people do not have proper training, education in loop tuning and process control. And so therefore, we'll just adjust this, adjust that. So right hands for proportional, left hands for integral. That's why we don't use derivative because we don't have a third hand. And so we just adjust it and, it's good enough. Okay, let's go. Let's do it. And so you got to ask yourself again. So there are other ways of tuning. Some of them are called quarter amplitude decay type tuning, which is then overshoot, undershoot, overshoot, undershoot, which is actually known as an underdamp response, meaning that it actually has an oscillatory behavior. What does that mean? Well, I change my loop, my set point, let's say, and it goes up and down, kind of cycles, and eventually might settle out. Now, the other thing we don't fully appreciate is that control loops, when the set point's fixed, is subjected to all sorts of variability.
Yeah.
So now we're looking at this from a frequency domain point of view. And so we're bombarded by all sorts of frequencies all put together, so anywhere from very, very fast frequencies, aka noise, to very, very, very slow disturbances, aka maybe seasonal changes, things that cannot change over, and everything else in between. What happens is that when you if you put in all those frequencies of variability that is present onto the PV, it will actually have a natural resonant frequency. I don't know if have you heard of Tacoma Narrows Bridge?
Yes.
Okay, so that bridge there, because that has a natural resonant frequency. I talk about also a car with bad shock absorbers. So you drive this car on a perfectly flat highway, not an issue. But now you drive this car, let's say in Winnipeg. You ever been in Winnipeg in March, April?
A lot of potholes.
A lot of potholes. Or Sudbury, another one there.
Or just Toronto.
Or just Toronto, yeah. What the heck, hey? So therefore, if your car has bad shock absorbers, you'd be subjected to all sorts of disturbances. Your car's going to tend to resonate at a natural frequency. And so now what happens now is that actually it's going to make things worse in automatic. It's going to amplify a portion of that variability and make it worse in automatic than on manual. Hence, that's why I always discourage the use of quarter amplitude decay or any kind of oscillatory type of response. So what I usually teach is it's called lambda tuning, which has been around for quite a while. But back to my NTech days, that is what we were applying. That's what my mentor, Bill Bielkowski, was able to, we were teaching that course. We were actually applying it, and became quite prevalent within the industry, especially in pulp and paper, and kind of made its way. But it's still nowhere near where it is. As I said, tune by feel is definitely the most common type of tuning method out there.
I definitely remember learning about, I think it was lambda tuning in school. We were doing all the math for. That was the part that I was excited about.
You're the first person. I don't know if you ever, did you watch my webinar? My last webinar was called Welcome to My Nightmare. Talking about Laplace transforms and how they actually apply there. That was a lot of fun. Actually, I had Alice Cooper there playing the music at the beginning. It was pretty.
I've definitely taken inspiration from you in your webinars for my webinar titles.
Oh, okay.
The music I have to add. That's
it makes a big difference actually. And at the end there, because at the end you got kind of the question, it's kind of coming in kind of sporadic.
Throw it in the background.
Throw it in the background a little bit. You can bring it up and down. So yeah, it's pretty cool.
We got one coming up on flame detection.
Oh yeah.
And there's a lot of good songs there that we can use.
Oh
so
yeah.
There's no shortage of fire.
Johnny Cash's song.
Yes.
The Ring of Fire.
Exactly. Amongst many.
Or the Bloodhound Gang.
I'm trying to think
I don't think you could play that one.
No, I'm trying to think which one we actually settled on. It might have just been the Ring of Fire. But anyway.
Yeah, awesome.
Nevertheless. So you did bring up an interesting point, though. Like you said, how each of these loops can be involved with upstream and downstream. And to me, that can become very quickly complicated. And so this facility you're headed down to, like what's your approach? How do you approach this? And how do you start making changes, knowing confidently that you're not making a problem worse downstream or upstream?
That's a very good point. So what I usually do is that actually, I said I'm going to go tomorrow in Sarnia. We're going to remote into their system in Cartagena, and what we're going to do is set up the data collection. So I use a tool called the NTech Toolkit. So, and hence it was acquired by Emerson, some Emerson product. We're going to be collecting data. So not off the historian. So I'm not a big fan of collecting data off the historian because the fact that it's compressed.
Okay.
And usually it's sampled very slowly. So you'll be sampled every 30 seconds, once a minute, 5 minutes.
That's not good.
I mean, I can go on and on about, I go on and on about that, and yeah. Don't want to go on that tangent right now. Talk about artificial intelligence and pattern recognition, all that stuff. Almost swore again. Almost swore. So where was I? Yeah, so we're going to collect data. Yeah. So here we set a boundary. This is around the reactor.
Okay.
Those of you know how to make carbon black. What you do is that you ignite very, very poor quality oil, and then you quench it right away. So what you're actually making a very, very poor incomplete combustion. Yeah. And there you're making essentially making soot. And then after that, they process it, they granularize it, and then you say, well, where do we use carbon black? Because actually carbon black is probably used in a lot of different stuff right here. You can make your tires last more than 5,000 kilometers, and 1,000 kilometers or so forth. But I digress. So yeah, we'll be collecting a lot of data.
Okay, that's
so over a period of maybe a week or 2 weeks, I'll be looking at this data to give me an idea as to what's going on, to look at the different kinds of relationships. Maybe there are valve-related issues. Maybe we're going to find, okay, we need to fix this right away. I'm pretty sure there's an issue there. And then look at interrelationships between all the loops that are set within that process.
Okay.
And then that will give me an approach. At least then I'm not coming in blind
Gotcha.
to the process.
And that's the software helps you analyze this.
Correct.
Too. You're
yeah.
not just looking at raw data.
I'm looking at raw data, but I'm looking at it from different perspectives. So it's called time series analysis.
Okay.
And so I will look at the data. I can look at it in different ways. I look just basically what's the average, the 2 sigma. So 2 sigma, it's a measure of variability.
Yeah.
So if you remember, for a normally distributed data set,
yeah,
95.2% of the data falls between plus or minus 2 sigma.
Gotcha. Okay.
And so that's an issue. So that's okay. Well, that I can see if it's high variability, low variability. After that, we look at power spectrum analysis, look at cycles and things like that. So if I see, look, I see that's got this, let's say an 80-second cycle. So again, so you go to vibration monitoring. They deal in hertz, cycles per second.
Yeah.
Process control, we deal in seconds per cycle, the inverse, because obviously our world is very, very on the other side of the equation.
Yeah.
And so I'll see, maybe I'll see 80-second cycle. And so, my whole downstream, there's an 80-second cycle here. Okay. And I can then quantify, and that 80-second cycle may be caused by a valve that sticks. So the valve is sticking, going up and down, up and down, up and down, causing variability, and it's impacting this control loop down here. So now, let's say, well, this is important loop. So therefore, I could say, well, if you fix this problem here, this is going to get that much better because of the interactions of the process. So I look at that, and then I could do XY plots as well, where I could do relationships. So for let's say valves for flows, I could see what the flow curve is. So if it's a quick opening, a linear kind of flow curve, and then make recommendations on how to actually improve the valve itself as well. Yeah, so once you do that, then you'll say, okay, so now I got a good idea. Go back and talk to so I'll be going down, and then I'll be actually doing some tuning after that. You talk to the people, obviously, you talk to the operators, you talk to the process engineers, just to get a good idea. Okay, all right, so again, I'm not a 100% expert on the process. You guys know.
Yeah.
So let's talk about how are we going to tune this, be able to make things better. And you just do your bump test, you do your calculations. Again, the NTech Toolkit does that for you.
Gotcha.
And off you go. And I was working for this chemical company down by Niagara Falls, and it's always funny because sometimes you always find out when things go wrong, but you never find out when things go right.
Oh, yeah, classic.
So I did some calculations for her almost a year ago, and I was talking to her last week, and then she said, oh, yeah, that's working great. It's like, okay, all right.
No news is good news.
Yeah, I guess so. Exactly. And then sometimes there have been cases where it says, do some tuning and come back maybe a month or 2 months or 3 months later and say, hey, your tuning doesn't work anymore. I said, well, it was working for a while, so
what happened?
What changed?
Nothing's changed. We didn't change anything.
Absolutely not. Yeah. Exactly. And so that's what happens a lot of times. You end up, your tuning doesn't work anymore. It's not the tuning, the process change.
Yes.
Something changed, right?
You have to adjust it.
And so to bring me to another point, actually.
Yeah.
So a lot of times, I always say, anytime you change a component within your control loop. So control loop, you got to think the output of a control loop goes to maybe a 4 to 20 milliamp.
Yeah.
So you make a change. It's got to go through your OPC database. Got to find the right controller. Controller's got to find your analog output, and then okay, I got to change that from 12 to 12.8 milliamps. That may go to I2P, possibly. I2P is an electro-pneumatic converter. If your valve speaks in pneumatics, not 4 to 20, then we need to convert that signal. And then from there, so there are issues right there. If you don't install them properly, you can install them and have 350 feet pneumatic tubing to the valve. Well, if you've lost dynamic capabilities. Then it talks to a positioner. So you got to think here, positioner is a critical component of a control valve. So you need to have a positioner. And so often, I've just been to some other plants, it says, let's go, there's a problem with this control loop, right? So let's go look at the valve. Look at the valve and say, well, there's your problem. There's no positioner. So and the positioner's job is to make sure that when I say the valve's at 50%, its job is to make sure it's at 50%. If we don't have a positioner, we have no idea where that valve is. No idea. So then the positioner then talks to the actuator, So you get different types of actuators there. You got piston, you got diaphragm actuators, and so forth. Possibly some frictional forces. That then actuates the valve, and the valve moves. Maybe it does, maybe it doesn't. From there, so you got packing, you got flow curves. Is it a butterfly valve? Is it a globe valve? Is it a ball valve? All that stuff. Then the flow changes. And another point I want to make, actually, now we know we got pressure control valves, we got temperature control valves, level control valves. The control valve changes one thing and one thing only.
Yep.
Changes flow. That's all it does.
Yep.
Right?
Totally.
So the flow will affect the pressure, flow will affect the level, flow will affect the temperature, but a control valve controls flow. So then after that, the flow changes or whatever changes, you measure it, you can get some signal dampening, filtering there, comes back to the control system, more signal dampening. But at the end of the day, the process, as far as the PID controller is concerned, starts at the output and ends at the PV. All components are part of your process.
Yeah.
So anytime you change one of those components, you will have changed your process. That warrants you to go back and look at the control system, at the tuning again. I've seen this in the nuclear industry. I've seen this actually. It was a power plant. My second day at Lakeside, I was at Lakeside. People said, we've got an issue, one of these valves, the power plant, that's actually now shut down, but they put in new Fisher valves, DVC positioner, everything else, and they were wearing out the packing. And so we're just looking at the valves going up and down, up and down, up and down, and it's like, okay. Turned out that the flow signal was a bit noisy, but the tuning was very aggressive. So it had a higher controller gain, meaning it would react quickly to deviations from set point. And what would happen was, since the flow signal was noisy, bouncing around, the control system was reacting, the PID was reacting to it, and the valve was going up and down, up and down, up and down. And I remember talking to our valve specialist, one of our valve specialists, the cycle times, in the DVC, you count cycles, how many times it changed direct, was in the millions, right?
Oh, boy.
And so the customer was obviously getting annoyed and so forth. And so what I saw was, okay, because the tuning was too aggressive. And the reason why it was originally aggressive is because the valve, the original valve that ours replaced, was very sluggish.
Oh, and they didn't change it.
They didn't change it. So it was very sluggish. So they needed to have aggressive tuning to overcome the sluggishness of the valve. They never changed it. So they replaced the valve, never changed the tuning. So all I did, I just retuned the controller right there.
That seems so obvious to me,
and just kind of calmed everything down. So tuning, you can tune it very aggressively. So tuning can impact also on the type of on the wear and tear on a control valve.
Yeah, the costs and
exactly.
It's interesting. You bring up a good point because I was thinking about this as you were talking. Was one valve to the next or one instrument to the next. We've seen this before where some vessels might have two different level technologies for redundancy's sake. And I said, well, while that's a good idea in theory, if you have, say, a DP level and a guided wave radar, there's going to be some disagreement there. And that disagreement is going to cause confusion amongst the operators. Which one do we listen to? Which one's right? And to be honest, even if you had two guided wave radars, if they were in this vessel, there was chambers, they probably would need separate chambers. Mm-hmm. You would also probably still have some disagreement there between there. I mean, pending everything wasn't exactly the same, but even still, you might have a little bit of deviations there, which again causes confusion and uncertainty. Can we trust the instruments or not?
Yeah, but the thing is there, you're measuring two different spots. Is the process exactly the same across? If it's a boiler drum? Absolutely not, right?
Yep. And the other thing that I've noticed too, and this plays a big part, is the basically the fluid mechanics behind their application in specific is that, the chamber had a certain diameter and then the connections, the top and bottom connections were at different locations and different diameters as well.
So was it installed the same? Maybe specified, installed, maintained?
Exactly. So, and it most often is not, right? And so one of them is having issues.
So let me ask you a question. So an instrument, what's more important, precision or repeatability?
Repeatability.
Awesome. Good answer. Ding, 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 ding. Good
Woo,
job.
I didn't know I was going to be put on the spot on this podcast.
Yeah.
because at the end of the day, right, it's you're going to use that information in those loops.
That's right.
And so if it's all over the place, right,
exactly that
you're starting with bad. And honestly, it brings up a good point that I'd written down earlier, was that coincidentally, I'm actually headed back to McMaster and get to do a lecture with some of the third years, I think they are, on instrumentation.
No kidding.
And it's something in university that, you know, you don't really think about, is you're given a lot of practice questions, and there's certain pressures and there's certain temperatures, and you're just given those and you work with those, but you don't think that, well, those pressures and temperatures, there's actually a lot that goes into getting those measurements, and there's a lot of uncertainty and errors built into those measurements. And then all the work you're going to do from that point on is going to potentially be based off of bad information.
Correct.
It has cascading effects, right?
Yeah. No, absolutely. And one of the things when I teach my basic instrumentation course, and is you were talking about instruments, and I always say, does an instrument actually measure that variable?
Yeah.
Right? And the answer is no.
Never.
Never. So a temperature doesn't measure temperature. We use the laws of physics to infer what that measurement is. Same thing with Coriolis, same thing with DP. So I always say you got to understand if you understand some of the basic of physics to be able to troubleshoot, but we don't actually measure those variables. We actually, the analogy is one of the slides that I show in my courses. I show a bunch of pine trees in the snow, and I say, do we see the trees? And I said, no, we don't. We see the shadow cast by the trees. We don't actually see the trees themselves. And so it's a very important distinction. No, it's an important distinction that we don't. See, well, that flow. It's well, no, we're not measuring that. So, and every technology has its limitations. And
definitely.
So let me ask you. So therefore, what kind of measurement uses Bernoulli's law?
Oh, you're stumping me. DP.
DP.
Whew.
Yeah.
I don't know if I was going to act that fast.
Exactly.
Yeah.
How about Faraday?
Mags.
Mags. Exactly. All right.
So
Ohm's law.
Well, RTD.
RTD, absolutely. And the Seebeck effect?
Thermocouple.
Thermocouple. Okay, all right.
So you're right, because it's funny. I mean, I even think about, part of our literature talks about Coriolis would directly measure mass flow. We directly measure density. And direct isn't exactly the right word, because we're actually looking at the delta T between the left and the right pickoffs for the Coriolis. Now, it is proportional to mass flow, and there is just some multiplier, and it is linearly proportional. But you're measuring delta T.
Exactly.
Right? You're measuring the frequency those tubes are oscillating at for density. You're not measuring density directly.
Correct.
And it's important, exactly like you said, to understand what could impact that to then potentially impact, the measurements that you're outputting.
I mean, you look at it like a vortex meter. He says, well, it's not reading. Is it because you're below 15%? You need X amount of velocity to create those vortices to be able to count them.
Vortex is a great example.
Yeah.
We see it across the board.
Yeah.
So I got a question back then. So, you've worked with many different control systems, many different data points. How often would you say that, customers are using the heart variables? They're pulling all these, because, most often you just get the primary, you just get it's the mass flow or the volume flow, but there's all sorts of other variables that are important for troubleshooting, and I assume loop tuning. Do you often get those?
No, actually. There's some places that do. Probably one of the most important heart variable to bring back, in my opinion, is valve position. Okay, so therefore you send a signal. What's the valve position doing?
And sorry, that's how you were when you're talking about hysteresis earlier. That's how you validate hysteresis, right?
One of the ways, or I could just do it looking at a couple of different ways. So if it's like a reasonably fast-acting loop, like a flow or maybe some sort of liquid pressure, maybe not a gas pressure, liquid pressure, I would do some bump tests and see how the process actually reacts.
Oh, I see.
Other ways to do it is that, and I always encourage people to do this, is that if you can, it's not always possible, but do the finger test. So I actually put my finger on the valve stem, and then with a radio or phone or whatever, call it in, tell someone in the control room, go up 1%, see if it's actually moving or not. You can feel 1%, you can feel 0.5% valves. So again, getting close to your process, knowing your process, critical. And I encourage all my students all the time, get to know, put your finger on the valve. I mean, sometimes it can be encapsulated in insulation, could be in irradiated area, or it could be like 200 degrees Fahrenheit or Celsius. So
maybe don't touch it then.
Don't touch it then. Yeah, I've had a few burns. But yeah, don't tell our safety guy.
Yeah, yeah.
Okay.
Well, trust me, I know. I've been at one site where these huge cooling lines that were above ground, and we're looking at a DP flow meter on it, and just but looking at the DP flow meter, you put your hand on the pipe, and you can feel the water ripping through this thing, and like I'm like, I don't know how fast it is, but it is fast.
It is screaming through.
And this, of course, this DP flow meter was there for 20 something years, and he goes, yeah, it hasn't worked right in a few years, and so touching the pipe, I look at him and I go, are you sure it's still there?
Yeah.
This is moving. I can tell this is moving very fast.
Yeah.
And that's definitely eroded over time.
Yeah.
If it wasn't properly installed, it could have snapped right off,
Yeah.
But so knowing the process, not touching that pipe, I wouldn't have said that statement.
No, exactly.
And
You can't.
Yeah.
You can't put a price on it in the sense that you see things. It's something.
Being out there, not just behind the control center desk.
I mean, some place, another place I've seen where, you look at this thing, it's like an octopus. It's like a complete octopus of piping, and there's a bunch of flow meters and valves there and everything else. Is like, because they didn't have the room, it was kind of a bit of a retrofit.
Oh, yeah.
And, but it's just a complete octopus, and it's hard to find, it's hard to trace out, and then, and 3/4 of the instruments aren't properly installed.
Yeah. I've seen that where like they just don't take apart the process. They built a new process around it, and it's like half those pipes aren't even in use anymore.
On top of that, you get a lot of dead bones.
Yeah,
exactly.
So I have to ask, have you been using ChatGPT?
A little bit here and there.
A little bit.
Yeah.
So, well, I bring it up only because when you have massive sets of data, right, the power of AI is going to be incredible, and I think what we can do with it is going to be really cool.
I agree with you. I totally agree with you. It's going to find its place, I think, in the process control world. I think is it going to replace? Probably not. We still got to rely on natural intelligence as opposed to artificial intelligence.
It's a tool.
It's a tool, exactly that. And so long as people understand that it is a tool,
it's not a replacement.
It's hyped up, it gets hyped up a lot. And I've seen this for a long, long time. I've seen trends come and go. So back in the late 80s, the biggest trend was SPC, statistical process control.
Oh.
And that was going to fix everything, and I can't remember. You look at deviations; it's statistical, and anyway, you had to do, but it did not take into account any kind of dynamics. So it's more on the static on the static side. Then after that was expert systems.
Oh, well, that sounds better than statistical.
Yeah, exactly. Expert systems came into play. And where they would apply fuzzy logic. And that was going to fix everything. That was going to be the amazing thing. It was going to try to mimic your best operator, and it's going to try to make recommendations on how to address certain situations. And it got its foothold in the mining industry, of all places, kind of strange.
Okay.
Because the mining is not usually the most progressive. They're catching up now, but it's not the most traditional, the most progressive type of industry. And so, we had statistical process control, expert system, fuzzy logic, and I still don't understand fuzzy logic, and I don't really care for it. And then now we're getting into artificial intelligence and so forth like that. And I think, like I said, it's going to find its place. And you're right about data sets, large data sets. Comes back down to the quality of the data again. So, I mean, we're talking about data compression, infrequency sampling. Have you ever heard of aliasing?
Like
data aliasing.
So, like one variable represents something else?
No, what happens is that your sample rate is much slower than the fastest variability within the signal. So what happens is that if I sample once a minute, when my PV is oscillating every 25 seconds, I'm going to see a different cycle.
Oh.
And that representation has nothing to do with...
really? That's a big problem.
Commonly, you'll see it, and you watch Westerns. Like it's an old Western movie, and you see the wagon wheel kind of spinning backwards. That's aliasing, because the frequency of the film reel is slow enough because of the spinning wheel spinning faster than it's actually taking pictures continuously. So that's why you see it going back and forth.
Oh, that's a good example, actually.
Yeah. So spinning wheels backwards. So data integrity. You got to have good data. Good representative data. The other danger as well, and I remember talking to this guy who was doing some AI work in process controls, a PhD guy for Spartan Controls, actually, a very smart guy. And we talked about how you could draw false correlations. So therefore, the paper machine breaks down, or this happens when Mercury is in this orbit. So it brings me back to a point, and there's a bit of a debate. I don't really follow all that much, but I know I've been reading like on LinkedIn, things like that, and just kind of where does a data scientist, whatever that means, I really don't know what that means, does a data scientist need to know some of the basics of what they're trying to model, analyze, whatever they're trying to do with it? And there's the debate, oh, no, data scientists, you just look at the data. And it just, like, to me, that's completely wrong.
Yeah, I see what you're saying.
I'd rather say, you got to know your data science, you got to know your statistics and so forth, and you got to know your process, what is it you're trying to analyze before, because then that kind of help you trying to look for correlations, but also not draw false correlations as well.
I could definitely see both sides of it, because you might be influenced to see things that aren't necessarily there than if you were looking at it blind. But if you are looking at it blind, right, you might just dig into noise and things that really don't matter, and you focus on the wrong things, right?
Correct. Absolutely.
Yeah. So I could definitely see both.
Yeah.
Huh.
Yeah.
You brought up a good point though about LinkedIn. So how do you stay up to date with the latest and greatest? You know, what do you do to learn more?
Usually I learn it's on site.
On the fly
on site, where there's no better kind of training ground, and like I said, I've been doing this for 35 years, and I still learn every day. It's just, oh my God, I learned something new. So I remember the first time I understood. I've been doing this for a while. The first time I actually understood how a boiler works, and it's like, oh my God! So they take the steam pressure, and then that affects they change the combustion rate to heat up the water, and then the water then measures and cascades to the feed water, drum level feed water. So it's not like they're process-wise, they're nested processes, but not directly connected, right?
Yeah.
And it took me, I remember that epiphany, and you're learning, you're there, you're supposed to do, so you got to learn fast, right? So one of the things I was like, oh my God, I can't believe that's how it works. And then it's like riding a bike. You never forget it after
exactly. That. Well, I do an intro to process controls for Lakeside's onboarding program. And honestly, it probably wasn't until I joined Lakeside that I really understood the dynamics of the control loops, right? And giving an example I like to give is when you're taking a shower. Right. That's an open loop that you're a part of, right? Yeah. When you turn that knob. Well, what are you actually turning when you turn the knob? Like, what's actually going on there? Like, you're trying to control the temperature, but you're turning a knob, right? And so now there's going to you can obviously get involved with the math side of it and understanding of how, well, I'm turning this a certain amount of degrees, and that's changing how much the cold and the hot water are combining together to then impact the temperature. But then what if somebody flushed the toilet? Or what if
a low disturbance,
throw a disturbance in here, right? Or your refrigerator, someone opens the refrigerator door, right? You're a disturbance to that refrigerator.
That's right. Yeah.
And so those are some fun examples that I go through to kind of talk about that. And then like you said, once you know and you understand, you can't ever look at things the same way again. That's always how you look at it.
Absolutely.
Definitely.
Absolutely.
So if people want to learn more about loop tuning, maybe give a shout out for your training you do.
The training, actually, next week I'm actually I teach 3 courses that I've written and I teach. So I teach Process Control Techniques 1, which I gave last month. That's AKA Loop Tuning 1.
Yep.
I teach Process Control Techniques 2.
Yep.
So that is next week. And there's still some spots available, but actually, by the time we broadcast this, it'll be long gone by then.
The next course will be
the next course, exactly that. Yeah, exactly. And then I also teach a basic instrumentation course as well, and I teach that both in person here. I could teach it at your site if you have enough people, or I'm also doing it virtual as well.
Nice.
And so all those 3 courses. People who want to get hold of me, sylvain.millette@lakesidecontrols.com. And that's it.
That's awesome. And you also host webinars.
I also host webinars, I kind of probably almost, I won't say I ran out of subjects, but I've taught a bunch of things. So you can actually, if you're interested, you can actually reach out and I'll send you the links. These are recorded. They're free. All you got to do is sign up with our platform, Big Marker, and you got to put in all your credentials, usually your social insurance number, your shoe size, and things like that. Just kidding. And there's a whole list, and you have a bunch of webinars on there as well, right?
Yeah, actually, that's a great thing. If you go to, it's pretty easy to find. Big Marker,
Yeah.
Google Big Marker Lakeside Process Controls. You just make an account,
Yeah.
and you can watch all of Sylvain's webinars, all my webinars.
And there's a bunch of even from on VFDs. if I'm
VFDs,
mistaken.
Mark Coombs one.
Yeah, Mark Coombs,
There's
exactly that.
There's no shortage of information there.
No, exactly. It's a great resource, great educational resource. It's something, you just watch them. I tell the people, if you go, just fast forward through all the boring stuff at the beginning and then
Get into the meat of it.
Get into the meat of it, exactly
Yeah.
that.
And it's all free.
It's all free.
It's all free.
How often you hear that, right?
Yeah. So well, thank you so much, Sylvain.
Thank you very much for having me. I appreciate it.
I
This has
definitely
been
learned a
it's been a
lot.
lot of fun, actually. It's
Yeah,
been just kind of free flowing. You do a good job. So good job.
Thank you, Sylvain.
Absolutely.
All right. Well, until next time, everybody.
All right.
Take care.
Take care. Bye now.